We've looked at volumes, obviously, in 2-unit and 3-unit for that matter. We're going to look at some other techniques. Now, the first technique is basically the 2-unit technique, but we're going to look at it in a little bit more depth. So that's why we call it by discs and washers. So basically, discs and washers is when we slice up our solid, and we're going to slice it perpendicular to the rotation of the curve. So if we go about the x-axis, there's my number plane, there's random curve, y equals function x, and I'm going to do the area from A to B, and we were going to revolve that round. Now, what I really do for this is I look at just one slice. Right? If you remember how we proved the area formula, we said we want to sum up all these slices as the limit approaches 0, and we ended up with the first principles formula, I think it was. And we were able to get it back there. So I've given it a bit of thickness so at least we can see it. But obviously that delta x, that change in x, again, we want as thin as possible. But if I was going to rotate that around, then basically I'm going to get a disc. Okay? And its thickness would be delta x. Now, because that's approaching 0, we can sort of think of it as a cylinder. And its radius would be the y value, which turns out to be function x. See, we need the radius in terms of the thickness. So if the thickness is in terms of x, I want the radius in terms of x. So whatever function x is, I'll plug that into the y value. And then we know the area of the cross-sectional face, well, that's a circle. And we go pi times the radius squared, pi times function x all squared. The change in the volume then would be the area times the change in the thickness. And this is called the element of the volume. So we don't normally do this with 2-unit. Normally we just jump straight to the formula. But in extension 2, we're saying, hey, where does it come from? So we need to come up with the element of the formula. And then we say, well, righto, delta V is the element. We're going to sum up all these elements going from A to B as the thickness approaches 0. Now, we saw before when we were originally doing it that actually that limit turns out to be the integral. And so from there, and that's what we then saw in 2-unit, pi times the integral. Well, we said y squared dx. I've just written function x squared there. So in 2-unit and 3-unit, fine, we can just jump straight to that formula. In extension 2, we're more interested in how we get there. So you don't just jump straight to the formula. Otherwise, I mean, it may as well be in a 2-unit question. It's more, how do we get there? Now, about the y-axis then is very similar. There's a random curve, y equals function x, but I'm now going to go around there. I'm going to slice perpendicular to the axis of rotation, so my slice will be horizontal this time. The thickness will be delta y, which means I need that radius, and the radius is the x value, but I need it in terms of y. So it'd end up being some function of y. I'd rearrange y equals function x to make x the subject. Okay, so our area, pi times the radius squared. Other than that, it's pretty much the same now. So therefore, this time out, my change in volume, my element of the volume, will be pi times gy squared times delta y. And I want to sum all of these elements up to come up with the total volume. In this case, I'm going from C to D. And there's our formula we end up with. All right, let's do an actual one. Y equals 4 minus x squared. So let's draw it. There it is. Upside down parabola. We're going to rotate about the x-axis. So I'm going to take my slice perpendicular to the x-axis. So there it is. Thickness is x. So I've got my slice. And yes, draw your slices. Okay, draw your slices. Because remember, we're building this. They want to see that you know how to construct the volume. Delta x. The radius is y, but we want it in terms of x. Well, we've got a lovely little formula up there. Y is 4 minus x squared. So area will be pi times 4 minus x squared squared, which means our element of the volume will be pi. I've expanded it out. 16 minus 8x squared plus plus x to the power 4 delta x, which means I'm going to sum all of those elements together. As if it was a 2-unit question, we probably would just jump straight to that step. From here, it becomes pretty much a 2-unit question. Add 1 to the power over the power, sub in, and there's our answer. So, I mean, your marks really is getting that from here to here. Well, that's just 2 units. You're not going to get many marks for that in an extension 2 question. It's creating that, how you get there. All right, but the beauty of this idea is we no longer are restricted to just going around the x and the y axis. We can go around any horizontal or vertical line. Theoretically, we could go around a line at an angle, but we're not going to do that. Okay, it's a bit more involved. So there's the same parabola, but this time I'm only going to go around the line y equals 3. So I'll need those points of intersection. Draw in the slice, but the slice will stop at y equals 3. Now, if I was to get that and rotate it, again, I'm going to get a cylinder. But the radius of that cylinder is not going to be the y value. It'll be y minus 3, the top boundary minus the bottom boundary. So whatever the y value is, minus 3, I need that in terms of x. So I'll sub in the formula for y, which is 4 minus x squared. 4 minus x squared minus 3. Okay, the radius of this is 1 minus x squared. Okay. So area will be pi times the radius squared. Element of my volume then will be the area times the thickness. And so I'm summing up, but this time I'm only going from the edge of the blue line there. So I'm only going from minus 1 to 1 because we're rotating around 3 there. And now we get into a nice standard integral that we can easily go and find. Add 1 to the power over the power. Substitute in. We're going to do one between 2 curves. 2 parabolas, normal parabola, sideways parabola. We're rotating around the y-axis. So my slice is going to go perpendicular to the y-axis, so it's going to be horizontal. And I'll try and fit in a little slice there. There it is. Squeeze it in. Point of intersection is 1, 1. We're going to need to know that. Now, if I'm going to rotate that about the y-axis, I'm not going to get a cylinder. I'm going to get a washer. Like so. A washer, for those that have never changed a screw or something like that at home, you know, those little bit that stops digging into the wood, yep, that's what we call a washer. So there it is. So we're going to need to find 2 radii. We're going to need to know what the outside radius is. Now I need it in terms of y because my thickness is delta y. So it'll be y to the power of a half. And the inside radius is y squared. So the area will be pi times, well, basically it's the large circle minus the smaller circle. And from there, it's pretty much the same now. Well, to get the element of the volume, I'll times that by the thickness, the delta y. Then we'll sum them all up. We're going from 0 to 1. And now we can create our integral. And again, a very easy integral to go and find. And there you go, 3 pi on 10 units cubed. Here's an HSC one. It's a nice one. Shaded region, x equals 1, y equals 1, y equals negative 1. The curve x plus y squared equals 0. It's just a parabola if you think about it, x equals minus y squared. So they've written it that way. That particular region is rotated around x equals 4. Now, they gave us a start. We want to find just the slice, and they gave us a picture of a slice there, and they cleverly called it S for segment, well, or slice. It sweeps out. They used a technical maths word where I said washer. They've said annulus. We're going to find the area of the annulus. Okay. Inside radius and outside radius. I've called the outside one capital R, inside one little r. Let's go back to the picture. We've got to be careful because we're going around 4. So the radius would go from 4. So the inside radius, the smaller one, would stop at the line 1. So I'm going to get a consistent inside radius of just 3. The boundaries, if you like, are x equals 4 and x equals 1. So top boundary minus the bottom boundary there. That'll be 3. Okay, so that's easy. Outside radius. Okay, what's it going to be? It's always tempting to say 4 plus the x value. But it's not. It's 4 minus the x value. Top bound doesn't change. Top boundary minus the bottom boundary. And if you hang on, that's going to make it smaller. No, it's not. Because the x value over this side is negative. So when you go 4 minus the negative, it's actually 4 minus minus plus. It becomes a bigger radius. Okay? So it's always top minus bottom. So that radius is 4 minus, so we'll end up with 4 plus y squared for the radius. Okay, so now we can get their area. There we go. Tidy it up and we match with what they wanted. Excellent. Hence go and find the volume. All right, well now I can say the elements of my volume, summing from -1 to 1. Now it's a nice easy integral to go and do. Add 1 to the power over the power, substitute in, and we have our answer. All right. Oh, it's just a handful.